Hi, my name is Delaney Farrell, and I am a student in the joint doctoral program between San Diego State University and the University of California, Irvine in the Computational Science Research Center. And my research is to constrain neutron star equation of state by using machine learning. Neutron stars are super dense, compact objects with masses ranging from 1.2 to 2 solar masses and radii ranging from 10 to 15 kilometers. For perspective, these stars pack more mass than the mass of the sun into a radius equivalent in size as the distance from SDSU to downtown San Diego. Neutron stars are the smallest and densest observed class of stellar objects, with densities of their core 10 to 15 times higher than the saturation density of nuclear matter. The internal structure of these stars can be described by the thermodynamic relationship between pressure and energy density, also known as the equation of state. A wide range of models for superdense matter exist because we can't physically see or measure what goes on inside of the cores of these stars. This range of models have been a topic of discussion in the astrophysics community for decades, as the equation of state tells us what macroscopic properties of a star are physical or not. In past, observations of stars have served as a tool to constrain equation of state. Determining a correct maximum mass of a neutron star can potentially eliminate entire families of equations of state. For many years, theoreticians hypothesized that the maximum mass of a neutron star was around 1.4 solar masses, but novel observational techniques like Shapiro delay found stars surpassing this limit. That meant that equations of state that predicted a maximum mass of 1.4 were completely ruled out. However, there's no direct link between observations of a star to its most likely equation of state. Equation of state is linked to mass and radius from a theoretical standpoint, and mass and radius are linked to radiation spectra from an observational standpoint. We propose using machine learning to predict an equation of state from observational properties of a star in hopes to place further constraints on the existing range of equation of state models. This would provide the astrophysics community a better understanding of the evolution of massive stars and about the fundamental building blocks of matter. From a theoretical perspective, a neutron star's equation of state determines macroscopic properties like mass and radius, as these are related through Einstein's field equations. An equation of state maps to a curve in the mass-radius plane, meaning that one equation of state can effectively describe a range or set of possible stars. The graphs below here on the left side show a mapping from equation of state over to mass and radius. Creating a relationship for the inverse of this mapping, or going from macroscopic properties back to equation of state, is much more mathematically complicated. And as such, very few numerical models exist to go in this reverse direction. From the observational standpoint, observed spectra is used to determine macroscopic variables. Neutron stars are detected from radiation, the most common being X-ray, gamma ray, or gravitational waves. X-ray emission from rotating stars known as pulsars are detected through powerful telescopes, one of which is called Chandra, which was launched by NASA in 1999. Chandra reads radiation spectra from a star, and this spectra can be mapped to the mass and radius plane by adding uncertainties based on assumptions about the star, like its atmospheric composition or a distance correction. Shown here on the bottom right is an example spectra from the quiescent low-mass X-ray binary X5, which was then matched to a probability contour in M and R. So why is this inverse mapping problem a well-suited problem for machine learning? When predicting an equation of state from X-ray spectra, there are a wide range of uncertainties to take into account. Even though the physics is incredibly complex, this is essentially just a regression problem, which deep learning techniques can solve very powerfully. We plan to implement a parameterized neural network that predicts equation of state as a function of the uncertainties that were used to formulate the X-ray spectra. To train our network, we use the nonlinear relativistic mean field model GM1L for the equation of state of the core, paired with BPB and BPS for the crust. X-ray spectra was then simulated using mass and radius values resulting from GM1L to match observations from Chandra using XSpec, which is a spectral fitting package developed by NASA. Shown here on the bottom right is an example of spectra that we have generated using XSpec, this one with uncertainty coming from the effective temperature. This project is being done in collaboration with many wonderful physicists and computational scientists. I'd like to give my advisors, Friedlin Weber and Daniel Whiteson, a special thanks. And physicists Lee Lindblom, Andrew Steiner, and Craig Heinke have helped me tremendously in understanding this project from the astrophysical side, while computational scientists Ashik Ghosh, Pierre Baldi, and Jordan Ott have been a big help from modeling this project on the Machine Learning Vantage. And this ongoing project is supported under NSF grants 1714068 and 2012152. Thank you.